I'm Thomas Jam Pedersen. I'm one of the co-inventors of a new nuclear technology that can transform the green energy space. We are in Copenhagen Atomics. We're big believers of this, what it says on the back of our t-shirts, energy equals prosperity. And we believe that there's lots of people in this world who would like to have the same prosperity level as I've experienced in my life, and even people who want to improve beyond that. Copenhagen Atomics has developed a new type of nuclear technology that is completely different from all the other types of nuclear technologies we've seen out there. One of the key benefits is that we can supply green energy at a lower cost than any other technology, and we're willing to do price matches. We can beat anything, fossil fuels, wind and solar, fusion, whatever, on price. And of course, that's an important game changer. The second thing, the nuclear industry has been used to a situation where the taxpayers and the governments was running the show. And we've seen some terrible situations in the past where huge cost overruns and very delayed nuclear power plant projects. We don't want to take that pathway. The projects we want to run, Copenhagen Atomics will finance, build, own, and operate the power plants. We will also decommission and recycle the power plants at the end of life. So it's a completely commercial nuclear power station. It's the same as you find with other energy technologies where it's also commercial plants, whether it be gas-fired power plants or wind parks or whatever. And then the third thing we list there is also really, really important. It's about the nuclear waste. Our new technology is able to take spent fuel from classical nuclear reactors and burn that spent fuel and get 10 times more energy out of it when we burn it compared to when the first reactors were using it. So it's phenomenal that we can now get so much additional energy out of that fuel instead of putting it in deep geological storage. And of course, the waste that comes out of our reactors are much less of a problem. It only needs to be stored for 300 years above ground versus the normal 100,000 years in deep geological storage. So it's really a game changer. And one of the reasons this technology is possible now is because we're using a new type of fuel called thorium. Thorium is a metal. It's an element in the periodic table. A ball this size made out of thorium can supply you with all the energy you need for your entire life. Not just electricity, but everything for cooking your food, heating your house, all the products you need, all transportation, your share of roads and houses and hospitals. So it's really amazing that you can get all that energy out of this little ball. And there's plenty of thorium on this planet. We will never run out of it. There's thorium in almost all countries of this planet. And the cost of a ball like this is roughly $100. So it's phenomenal, and it will change the energy sector. The second thing we bring into this equation is that we're going to mass manufacture these reactors on assembly lines. So it's not like the classical nuclear reactors where it's built on site and it takes 10 years and they employ 5,000 people or whatever. We build them on an assembly line just like we build cars and airplanes. We can build one reactor every day. And these reactors fit inside roughly the same as a 40-foot shipping container, so you can easily move them around on trucks. So that's, again, a game changer. This is a picture of what a nuclear power plant like ours look like. In this case, it's a 1 gigawatt nuclear power plant. And the building we built is similar to any other distribution center that you see in logistics companies. We humans can build those buildings in 2 months. And then inside you see an array of nuclear reactors. In this case, for 1 gigawatt electric, we need 25 reactors on a row, and we need a few extra boxes to be able to swap things in and out during the lifetime of the plant. In the next couple of pictures, there are some close-up. And one of the things, in these new type of reactors, inside the reactor building, there's not supposed to be any humans for the 50 years that the reactors are operating. We operate everything remote controls, the cranes. We will have robots in there that are remote controls. So no humans in the building, so no problems with humans making mistakes. And there's some more pictures of what it looks like. So the building in the foreground is what Copenhagen Atomics supplies and build, own, and operate. That's the nuclear power plant itself. And then we generate heat, and then that heat needs to be converted into electricity. So the things you see there in the background, the buffer tanks, the big round tanks, and the steam generators, and in the buildings in the background, you would have the steam turbines. Those things behind our building is operated by other companies. We only operate the nuclear building itself. Then there's this overview, and this really tells you why this is a huge game changer for the, first of all, the green transition, but also for the energy sector as a whole. When you compare the amount of energy you need to put into a system versus the amount of energy you get out of the system throughout the lifetime, it's really game-changing. On the right-hand side, the orange pillow there is the Copenhagen Atomics waste burner. We are at least an order of magnitude more efficient than any other energy system that we compare to. And the purple one called LWR, that's short for light water reactors. That are all the traditional reactors that are built all over the world. We have roughly 400 of those. And then all the hydrocarbons, and then of course wind and solar. And the fun thing here is I go and make these speeches, and then people say to me, oh, but the wind and solar numbers are wrong, they should be 4.5 or something, and I'm like, you know, even if we were to double those numbers, which is from physics completely impossible, but it still doesn't matter. It won't be competitive in the future, but for now it's good. We also, a lot of times, we are asked to compare this new type of nuclear technology that we are developing to the more classical nuclear technologies. And on the left-hand side in this table, we have our Copenhagen Atomics waste burner technology. On the right-hand side, we have the traditional uranium-based light water reactors. And I understand that Poland, for example, have just decided to build 10 of those power plants on the right-hand side. Then in the middle column, we have sort of what is commonly termed uranium-based molten salt reactors, and sometimes they're called advanced reactors. So we try to make some comparison between those. And of course, the first row is about mining, and you see how big the difference is. For traditional light water reactors, we need 100 times more mining to run the same amount of energy production. And of course, all that mining costs energy, and then you have to transport all those materials to somewhere where you do the refining of the materials, and then you have to do the enrichment, which is also an expensive process and very delicate. So just the two first lines, you see that there's a huge expense for traditional reactors. It's typical for traditional reactors that they need to load 20 tons of uranium every other year. So it's an ongoing process for a lot of fuel production. And again, if you look at the waste storage down here, we only need to store our waste for 300 years above ground versus the other ones that needs to store it for 100,000 years. So really a game changer. And of course, all of this translates into the energy price. In general, we say that we can be 4 times cheaper than traditional nuclear power plants, the ones that are being built today, and we can be half price of the so-called advanced nuclear reactors. And that's why we say very confidently that we can beat anyone on price. But I think really, really the important thing here is to take home is the deployment speed. We can mass manufacture these reactors and install them really, really quickly. This is something that nobody else can do. One of our production lines, or one of our assembly lines, can install 15 gigawatts of electricity per year. There is no other company or no other country in the world that can currently install 15 gigawatt of electricity, green baseload electricity per year. So just one assembly line can really rip. So a lot of times people say, oh, but nuclear is dangerous. And actually, I don't know where the majority in the public got that idea that nuclear is dangerous. It's so far away from the truth. These are numbers from international studies, and they are put out again and again. And you can see that nuclear energy down here is on par with wind and solar. And this is even including the death from Chernobyl and Fukushima. And if you compare, a lot of times, if people want to install a new power plant, they're thinking, should we make a nuclear power plant or a coal power plant? A lot of times, that's the choice, coal or nuclear. And you can see that coal-fired power plants is, when you measure it in death per terawatt hour of electricity manufactured or produced, It's 1,000 times more dangerous. It's not like a little bit more dangerous. It's 1,000 times more dangerous. Like, I don't know why people call nuclear dangerous. And this is even including some of the accidents we had. And I don't know if you guys know this, but the reactors that were used at Chernobyl when the accident happened, there are still 8 of those reactors running today. And they have been running now for 40 years. Do you know how many people they killed in those 40 years? 0. 0 people. So this is considered the most dangerous reactor we have in the world, and many people have asked us to shut them down because it's dangerous, but still, they haven't killed a single person, and I admit that it's not a perfect design, and the stuff we make today is much, much better, but still, there's no coal-fired power plant anywhere in the world that can claim that they killed 0 people during their lifetime. So in comparison, I don't get it why people call nuclear dangerous. Then I want to talk a little bit about nuclear waste, because a lot of times that's misunderstood by the majority of the public. So this icon up here represents spent nuclear fuel from classical nuclear reactors, and it's radioactive, yes. If you look inside that drum, what is actually in there? 95% of the atoms in there are uranium atoms. They are exactly the same atoms as what we got out of the ground many years earlier from mining. They have not changed at all. It's not super dangerous. They are radioactive, but you can eat it and you won't die from it. The uranium atoms. But the other part that makes it problematic is these 5% up there. They are fission products and then long-lived actinides. And they are dangerous, to be frank. And what we can do there is we can separate that out and take the orange part, the 1% is long-lived actinides and plutonium. We can put that into our waste burners down here, and then we mix that with thorium, and we make it possible to burn that nuclear waste and turn it into fission products. Fission products are still radioactive, but they only need to be stored above ground for 300 years. So we turn a problem that is very expensive and very difficult to solve for politicians into a problem that is manageable and where we know the solution for storage very well. I should say that it's expensive to do this separation, and it has been known for many years how to do it, but it was just too expensive for the old regimes to do it economically, and that's why we did not do it. But because we can make a lot of money from the energy that we produce, we are now able to pay for this process of separation, and in this way we're able to solve this problem with the spent nuclear fuel. Then you might ask, okay, so that's great, but when is this technology coming? Copenhagen Atomics is already building the first thorium reactors in Copenhagen and testing them. We are the only company in the world currently building full-scale thorium reactors. We plan to have the first demonstration reactor ready in 2025, and we plan to have the first commercial reactor ready in 2028, and then shortly after that we will start the assembly line production. And right now we are looking for a first few select countries to be the first ones to install this new energy source. Of course, there's a limit to how much we can produce of this in the beginning, so we can only supply maybe 1 or 2 countries in the beginning, and that's what we are negotiating right now, which countries should be the first ones. And I hope there will be a European country among those. And also, we are looking for investors. We think this technology can easily make 100x on return on investment for investors who invest now, sort of 100x in 10 years. So that's, yeah. So if you're interested in investing or hearing more about this technology, then feel free to come to our booth. It's right around the corner out here. And that concludes my talk.